All right, welcome everyone. Today we're going to be talking about arc length, again, this time in Cartesian coordinates. So last time we saw how to calculate the length of a polar curve. This time we'll see how to calculate the length of a curve that's given in Cartesian coordinates. So let's start with the formula. And here we have our arc length formula. So now we're given a curve back to regular x's and y's, y equal to f of x, so y as a function of x, where we're looking at some interval over some interval, so x is between a and b. All right, so how do we find the length of this curve? Well, it's equal to the integral from a to b of the square root of 1 plus the derivative dy dx squared. And then we're integrating with respect to x. So x is our variable, we set up our integral, and we're going to be integrating with respect to x. Now there is one kind of extra condition here. We need this derivative, so we need f prime or dy dx, whatever we want to call it, needs to be a continuous function on this interval from a to b. So sometimes when we differentiate, normally, if we're going to run into issues with this, normally what happens is we differentiate and we get a fraction, and then we have potentially division by 0. Normally that's where we see this. There's other ways it can happen, but normally for our purposes what happens is we have a function, we differentiate it, all of a sudden we have a fraction now, we might have division by 0. So we just want to keep an eye out. So if you're differentiating, if you see fractions, just kind of keep track of where you're dividing by 0. Can't be inside that interval or at any of the endpoints. So we have to be all clear on this interval from a to b. All right, so here's the formula we're going to use. Now there is a slightly different version. So we can specify a curve y equal to a function of x. We can also specify a curve in Cartesian coordinates. So a second version to this is where we have x as a function of y. And y is between, some numbers c and d, let's say. So this is another way to specify a curve where instead of having a function in terms of x, we have a function in terms of y. So x equal to g of y, where y is between two numbers c and d. So this is another perfectly good way to describe a curve in Cartesian coordinates. And the formula for length here is very similar. It's going to be the integral from c to d of the square root of 1 plus, and now we're going to actually be differentiating with respect to y. So we're going to have the derivative dx dy here. And we square it, add 1, all under the square root. And with this version, when we set up the integral, we're going to be integrating with respect to y. So that's just one little thing to keep track of. The differential here should match up with the variable of your function. So same thing here. The dy here should match up with the variable of our function. So we just want to keep track. All right. Let's try a few examples. Here's the formula. We're gonna look at a few examples. And then if we have time, we'll actually kind of talk a little bit about where this function, where this integral, where this formula really comes from. So we'll kind of sketch out how we might actually construct this formula in some sort of proof. All right, so let's start with a few examples though. So we're given the curve y equal to 1/2 x squared between the points 0, 0, and 2, 2. Again, we're back to Cartesian coordinates here. And we just want to set up the integral that gives the length of this curve. All right, so let's write down our formula. The length is going to be the interval from a to b of the square root of 1 plus the derivative dy dx squared. And we're going to be integrating with respect to x. So why are we setting this up with respect to x? Well, we're given y as a function of x. So all of the action here is happening on the right, and x is our variable. All right, so what does this mean? Well, we need to calculate the derivative, and then we also have to decide on what our limits of integration are going to be. And so this differential tells us x is our variable. So when we're given these points, we're looking at the section of curve in between these 2 points. Because x is our variable, we have to use the x coordinates. Now we get kind of lucky here in that the x and the y coordinates are the same, but we're technically using the x coordinates here because x is our variable. All right, so let's set this up. It's going to be the integral from 0 to 2, the square root of 1 plus, and let's just calculate our derivative. So what is the derivative here? Well, if y is 1/2 x squared, the derivative, dy dx, is going to be 1/2 times 2x. So just doing power rule on that x squared, you can probably just do this in your head. Simplifies to just x. So let's fill that in here. So it'll be the derivative dy dx squared. So we're going to end up with an x squared here. All right, so the problem just said to set up the integral. That's our integral all set up, ready to go. If we wanted to keep going with this and actually calculate the arc length, calculate this integral, well, we see a square root, and we see 1 plus our variable squared, 1 plus x squared. So we should be thinking here trig substitution. So when we have 1 plus our variable squared, the trig substitution is a times tangent theta. The differential dx, if we need to convert that over, would be a times secant squared theta, d theta. And then that square root term simplifies into a times secant theta. And here a is just the square root of whatever constant you have here. So in this case, our constant is a 1, so the a value would be 1. So the square root of whatever number you have there. So the problem here just said to set up. So we only went this far. But, spoiler, there's going to be a homework problem where you have to do something like this. So trig substitution. Calculate this integral of 1 plus x squared. And this is the steps that you would kind of use. All right. Let's try another one. Set up the integral, and then we'll actually calculate this one. Just to review some other kind of integration techniques. So here we're given the curve y equal to x raised to the 3/2 power, where x is between 1 and 3. We want to find the length of this curve. So let's kind of, we know what pieces we need. So let's actually calculate these off to the side, and then we'll go through the main section of our work. And so it helps to sometimes do the derivative squared just off to the side. Work with the piece that's under the square root first. Then once you've simplified it as much as you can, plug it into the integral. So we're going to start with y equal to x raised to the 3/2. Let's calculate the derivative of that. So what is the derivative? Well, power rule. So bring the 3/2 down, keep x the same, subtract 1 from the exponent. So the derivative is 3/2 times x raised to the 1/2. All right. Now we know our length formula here has the derivative squared, so let's square this thing. So we're squaring everything. Everything. So, and I forgot the squared. Squared. We got to square it. And so we have a constant here times a variable part. That multiplication, we have to essentially distribute this exponent when we have multiplication. So we're going to square the 3/2, and we're going to square this x term. So that's sort of a common mistake. Just remember, we need to square both of these because it's multiplication right there. So when we do that, we get 9/4. And then when we square the x to the 1/2, multiply the exponents. So 2 times 1/2 is 1. We're just going to get an x. All right, so there's our derivative squared, and we've simplified it down. So let's set up our length formula. So the length is going to be the integral of the square root of 1 plus this derivative squared. So let's just use our simplified version here. Well, you know what? Let's write out our formula. Good practice. All right, so what is our derivative squared? Let's fill that in. 1 plus, and I never write my square root signs long enough. 9 over 4 x dx. And we have to decide also on our limits of integration. And here, this is nice. We're given the interval. So lower limit is 1, upper limit is 3. All right, so this is going to do it. If we can calculate this integral, we're going to get the length of this curve. Now, we have a square root, so there's no way around it. We're going to be having to deal with this square root in all of these length calculations, and that's going to be the difficult thing. So sometimes, like we saw in example 1, you might have to do a trig sub. Here, we can get away with a regular u substitution because this, the term under the square root here, while it's complicated, a u sub works. So let's actually, we're going to let u equal what's under the square root. So 1 plus 9 over 4x. We're going to calculate our differential for this substitution. So differentiate this, we get 9 over 4 times dx. And if we look, in our integral here, this 1 plus 9 over 4x, we know what that's going to do. It's going to become u. And then the dx here, we need to convert that over as well. And if we look down in our differential equation down here, du is equal to 9 over 4 dx, we need to solve for this dx. So we want to know what dx is. So we're going to multiply both sides of this equation by, the reciprocal of 9 over 4. So we're going to solve this for dx. So we're going to get 4 over 9 on the left times du is equal to dx. So we're just multiplied both sides of this equation by the reciprocal. All right, so now we know what dx is going to be. It's going to be 4 over 9 du. So essentially, we're just going to plug in all the pieces here. And when we do this, we have some choice about the limits of integration. So we can either convert the limits of integration over into u, perfectly fine to do that, or we can leave them in terms of x. I kind of like that approach. Either way is fine, though. I'm going to leave them in terms of x. So just to really emphasize that, though, I'm going to now write them x equals 1 and x equals 3, just to remind myself that once I get this integration done, I'm still going to have to convert that antiderivative back to x before I plug in. All right, so let's get the antiderivative here. And maybe before we do that, let's move that 4 over 9 out in front. And let's rewrite that square root function as a power function. So we're going to write it as u raised to the 1/2 du. Makes it a little bit easier to integrate there. Now we can just do the antiderivative. So we'll have the 4 over 9 in front. Let's get the antiderivative. So we keep our variable the same, u. Add 1 to the exponent, so we go from 1/2 up to 3/2. Take this new exponent, flip it, put it in front, and there's our antiderivative. Now we want to convert this we didn't do anything with the limits of integration, so we want to convert this antiderivative back to x. And while we do that, let's just simplify these coefficients. So we're going to have 8 over 27, and then we're going to end up with 1 plus 9 over 4x raised to the 3/2. So I just switched this u here and changed it to a 1 plus 9 over 4x. And now we're going to evaluate. So top number goes in first. We end up with 8 over 27 times 1 plus 27 over 4 raised to the 3/2 power. And then we take our bottom number, plug that in. We get 8 over 27 times 1 plus 9 over 4 raised to the 3/2 power. And then we subtract. And we can simplify this down if needed, but perfectly good answer right here. There we go. So we're able to calculate the arc length for this curve. It took a little bit of work to get there. We had to do a little bit of u substitution. Good review there. But we were able to do it. All right. Let's try another one just for the practice. And this next example, arc length is kind of difficult to calculate for general functions. And the reason is because of this square root function. So square root functions are, as we know, we did it. Probably well, it's not the most fun section, the trig substitution section. We know square root functions are tricky to integrate when things go right. So for a lot of these problems, there's a little trick that we're going to see. And the trick really solely exists because it's going to get rid of the square root function. So there's these types of examples here, and you're going to see a few of these in the homework, where we get kind of lucky and we're able to factor this. You know, once we work with that the formula, we're able to simplify this down. So there's going to be a trick here. And you want to keep this in mind when you're trying these problems on yourself. And really, the reason why we see a lot of these examples with this trick is because it gets rid of that square root function, and we're able to kind of have an easier integral to do. So just keep this in mind. It's really a trick. It only works for these types of problems here. It doesn't work in general. Well, let's just see what it looks like. So we're going to find the length of this curve, x equal to y squared minus 1 over 8 times the natural log of y, where y is between 1 and 5. Now we're given x as a function of y, so we're going to use that other version for arc length, where it was in terms of y. Very similar setup, though. And so when we do this, it's going to be helpful to try and work with the, that square root term first. Get it simplified as much as you can. All right, so let's do that. Let's actually find the derivative of this function. We're going to be differentiating x with respect to y. So let's differentiate this. So we get 2y minus 1 over 8 times 1 over y. So derivative of y squared is 2y. Derivative natural log y is 1 over y. Let's kind of just go through and kind of build up what's underneath that square root function. So we know we need to square the derivative, dx dy squared. So let's square this thing. We need to square everything. And to help with this, it may be helpful to write out 2 copies of this and use FOIL to multiply them out. I haven't decided if I want to write this as 1 over 8y. I think we're going to keep it as 1 over 8 times 1 over y. We could combine these into one fraction. All right, so we're just we're squaring this, so we've written out 2 copies. And the reason for this is then we can just do FOIL. So let's take the 2y here and multiply it with the 2y over here. What do we get? We get 4y squared. Then we multiply the 2y with this negative 1 over 8 times 1 over y. And when we do this, the 2 times the negative 1/8 is going to give us negative 1/4. And then the y times 1 over y is just going to give us 1. So we're going to get negative 1/4 from multiplying this 2y with this term here. Same thing right here. When we multiply the inner terms here, negative 1 over 8 times 1 over y times the 2y here is going to end up with another negative 1 over 4. And then finally, we multiply the last terms together. So there's going to be 2 copies of negative 1 over 8. So we're going to end up with positive 1 over 64. And then there's 2 copies of 1 over y. So we're going to end up with 1 over y squared. And if we simplify this down, the negative 1/4 and the negative 1/4 simplifies to negative 1/2. Okay. Now, let's keep an eye on this negative 1/2. This is where the magic is, the trick here is going to happen. So keep your eye on this negative 1/2. So what's the next step for our arc length? Well, we have our derivative squared, and then we would add 1 to it. So what happens when we add 1 to this? Well, this negative 1/2 here, when we add 1 to it, it's going to become positive 1/2. So that 1 minus 1/2, that 1 plus this negative 1/2, that's going to become positive 1/2. And we'll put it right in the middle there. So notice, going from the derivative squared, we had a negative 1/2. And then when we added 1 to it, everything else stayed the same except we ended up with a positive 1/2 here. So this is the trick, and we just get kind of lucky here, and that's really why we see these a lot of the time for these arc length problems, is because we're going to get lucky, and this thing is going to factor, and it's going to factor into a perfect square. So when this negative 1/2 changes into a positive 1/2, how does this thing factor? Well, it factors almost back to exactly what we had before. The negative here is just going to change into a positive. So, this, like I said, this is just a trick that we see a lot of times in these examples. So when this negative, it's a magic trick. So when this negative switches to a positive, we know how to factor this. So we know how to factor this, and it factors exactly the same way as what we had before, except this negative switches to a positive as well. So when this negative here switches to a positive 1/2, this negative in our factored form switches to a positive, and we're able to kind of refactor this, which probably would not be obvious. I don't think it would be obvious to me that this thing would necessarily factor. But it does, and it factors very nicely, and it factors into this perfect square. So we're taking this dx dy squared, which kind of is already factored, and it has this negative. Essentially what's happening when we add this 1 is it's staying the same factor, it's just changing into a positive. So it's very unique here. This does not happen all the time. All right, so why is this kind of a trick to notice this? Well, because then once we set up our arc length formula, the square root and the squared are going to cancel, and we get rid of the square root, and then it just becomes an easy integration problem. So let's set up our integral. It's going to be the integral from 1 to 5. And let's just say this is the length. It's going to be the integral from 1 to 5. The square root of 1 plus the derivative dx dy squared. And we're going to be integrating with respect to y. Now we know we simplified. We worked with this 1 plus the derivative squared. We've simplified it down. So let's just use this simplified down version. So it's going to be the integral from 1 to 5, the square root of 2y plus 1 over 8 times 1 over y squared. The square root and the squared are going to cancel. So we just multiply the exponents there if you want to think of it in terms of power functions. So the square root and the squared cancel. So we're left with just the integral from 1 to 5 of 2y plus 1 over 8 times 1 over y dy. And this integral is not too bad. We can do this one. No trig substitution, no u substitution. We can just do this one. What's the antiderivative of 2y? Well, it's just y squared. What's the antiderivative of 1 over 8 times 1 over y? Well, that's 1 over 8 times the natural log of absolute value y. We evaluate this thing from y equals 1 to y equals 5. Top number goes in first. We get 25 plus 1 over 8 natural log 5. We can drop the absolute value because 5 is positive. Plug in our lower number, 1, and subtract. So we get 1 squared plus 1 over 8 times the natural log of 1. And the 1 is positive, so we can drop the absolute value sign there. And actually, natural log 1 is 0. So this whole kind of second piece here would be 0. We'd only have this 1 squared. So if we simplify, we would end up with 24 minus 1 over 8 natural log 5 as our arc length. All right, so there we go. All right, so some of these, you're going to see it in the homework. This is really a trick. So just to kind of be aware of, if you're going along and you weren't aware of this trick, I would kind of consider this a little, it's tricky. It doesn't immediately jump out at you that this thing is going to factor. Maybe if you sat there and thought about it a little bit, this would factor. You'd be able to do it. But just be aware that when you see this, when you're going along, it helps to kind of work this out step by step. So start with the derivative, then square it, then add 1 to the derivative squared. And when you're going along, and when you add that 1 term in, so when you add this 1 in, and you see that you go from a minus 1/2 to a positive 1/2, think this, remember what we did, and realize that the expression is going to factor in exactly the same way. So 2y, 2y, 1 over 8 times 1 over y, 1 over 8 times 1 over y, both are squared. The only difference there is this minus is going to switch to a positive as well. So just to be aware of that. So it's a little trick for these problems, and it just helps to get rid of that square root function. All right. I think we'll stop there. I was going to go through and see how the arc length formula is kind of constructed, because we can actually do it. We can actually see where this arc length formula comes from. But maybe we'll save that for another time. So, all right, let's stop there. Have a nice rest of your day, and then we'll see you next time. Bye-bye.